Okay, so we are finishing this material on functional analysis with a section on commutative Banach algebras. Just a two-lecture introduction to be followed by the final lecture on the measure and integration handout that I handed out. So the idea is to add to our discussion of Banach spaces the notion of multiplication and where that fits in. Not just any multiplication, you need some sort of continuity of multiplication operation. So we're going to have a particularly strong condition on the norm in order to make it be compatible properly with the multiplication we're dealing with. And that multiplication brings in some extra structure, which means that you get a rather different theory from the theory of Banach spaces on their own. Now, we're most interested in Banach algebras as complex vector spaces and complex algebras. So most of the time we'll be working with the complex numbers in this section. And again, there's a theory of general Banach algebras, but we're mostly going to be interested in the commutative Banach algebras, which has its own flavour again. And also, you can study Banach algebras without identity elements or with identity elements. And most of the time, we'll work with Banach algebras that have got an identity element. So something that acts like 1 when you multiply by it. So one example to bear in mind, even though we haven't yet defined a Banach algebra, is the continuous complex-valued functions defined on a compact Hausdorff space. Now, we already discussed this earlier, and it's a Banach space using uniform norm. So the uniform norm, norm f infinity, which we can also write as mod f sub x, as the supremum of modulus f of x, where x is allowed to be in X. So that's our uniform norm, and that makes this into a Banach space, but you can also multiply continuous functions together point-wise. You can add them point-wise, you can multiply them point-wise. And it turns out that that's completely compatible with this norm, and so this becomes one of our favourite examples of a Banach algebra. This and subalgebras of it, because you can take multiplicatively closed linear subspaces of this, and you'll get subalgebras, and they're interesting as well. And as I say, we're focusing on commutative Banach algebras. If you want a non-commutative Banach algebra, which we won't be talking much about, then you can look at bounded linear operators. We already know that's a Banach space when E is a Banach space. So as you start with E being a Banach space, and then you take B of E, remember, is our shorthand for B of E, E, the continuous linear operators from E to E. And we know that's a Banach space because E is a Banach space. But you can also multiply operators, but the multiplication is done as composition of operators. So ST equals S composed with T. So ST of X is equal to S of T of X. So that's different from pointwise multiplication, because you say do the right-hand operator first and then do the left-hand operator. And that's usually different from doing the left-hand operator and then doing the right-hand operator. We have assessed coursework for D1410 here, but I've made spare copies so that if you take a copy also there, because it might be useful to look at for everyone else as well. It talks about concepts that we will be discussing tomorrow about measure theory, so it's worth looking at anyway. But for those people doing topics in analysis, it's the assessed coursework sheet. So bounded operators from E to E is a nice Banach algebra in this way. Again, we haven't defined Banach algebra yet, that's coming up. But you can think of these as two typical types of examples. One of the typical commutative Banach algebra, and the other one is a fairly typical non-commutative Banach algebra, assuming E's got dimension at least 2. So Banach algebras have more structure to Banach spaces. So there's quite a lot of theory that's special to Banach algebras which you wouldn't discuss for Banach spaces. So even though if you Banach algebra is a Banach space, you wouldn't say, so it's just part of the theory of Banach spaces. There's more to it. And similarly, there's B of H, C-star algebras, and so on. They've got their own theory. Even though they're all examples of Banach algebras, still, they've got their own flavour. Okay, so what's a complex algebra? Well, you just start with a vector space, but it should be a ring with respect to multiplication. Well, a ring means you've got an associative multiplication and you've got the distributive laws. So the difference between a ring and an algebra is that it's also a vector space and the multiplication operation is bilinear, which boils down to the following. So as well as having the distributive laws and the associative laws and so on, also multiplication works here. Alpha, the complex number, A and B are in the algebra, and you can either multiply A by alpha, or you can multiply B by alpha, or you can multiply the product by alpha. It all ends up being the same thing. This is slightly different from saying that there's a copy of the complex numbers as a sub-ring of your algebra. It's slightly more sophisticated than that. The complex numbers, in as much as they're multiplying by the complex numbers, that operation sort of got to commute. If you're thinking of it as a ring, and if you did have a copy of the complex numbers in there, those complex numbers should be in the centre. They should commute with everything else in your algebra. And that's a big difference. If you look at something called the Quaternions, you might think that's a complex algebra because it's got various copies of the complex numbers in. But it's not an algebra over the complex numbers because the complex numbers aren't in the centre of the Quaternions. So that stops that being a complex algebra. Anyway, that's in case you do look at the Quaternions and wonder where it fits in. It's a real algebra, but not a complex algebra, the Quaternions. Okay, so mostly we want to have an identity, which in general you normally denote by E, but which we'll often denote by 1 as well. If you've got an identity, then that means a multiplicative neutral element, an element that whenever you multiply it by something leaves it unchanged. So for every A in the algebra, we should have EA equals AE equals A. Will mostly be commutative, so you only have to ask that one way round. And commutative, of course, means that the products are the same either way round. And under those circumstances, then having an identity, you only have to have your equality one way round. So you can do real algebras, but we're not going to worry about them so much in this section. But you just replace every mention of the complex numbers with the real numbers in what I've just been talking about. If you've got an identity, it's standard that that's unique, so we call it the identity of A. And then we'll often denote it by 1, but you've got to watch out to make sure that you have to know, are you talking about the complex number 1, the constant function 1, the identity element of the algebra, and so on. In context, you should be able to figure out which is which. But I did insist that E is not 0. So you see, there is a trivial algebra which just has 0 in it. And add anything or multiply it and you're still 0. And that's also a vector space. And it is a perfectly good complex algebra, but we don't want to count it as having an identity, even though it is actually true that 0 times anything is equal to it in this particular case. That's why I wanted to insist that the identity element should not be 0. There's a split in the literature, but most people would agree on that. So we're going to do complex normed algebras, complex Banach algebras, and anytime I talk about that, if you want to know what real normed algebras are, you just replace complex with real, and you can get the same definition. So here is the bit where you insist on the multiplication being compatible with the norm, or the norm being compatible with the multiplication. It's pretty much the same as saying that multiplication is continuous as a map from A cross A to A. And it's actually the same as that up to a constant. But we'll insist on the slightly stronger condition that the norm is submultiplicative, which means that the norm of AB should be less than root of the norm of A times the norm of B. You won't get that for free in a typical setting, but it will be quite common for it to be less than root of a constant times that, and under those circumstances you can renorm using an equivalent norm and fix it to make it submultiplicative. But certainly for normed algebras, you may well end up with coming across multiplication that isn't even continuous from A cross A to A, and where this fails completely and can't be fixed. Banach algebras, that's far less common. So what's a Banach algebra? It's just a normed algebra which is complete of the normed space. Oh, and this unital business. Unital is a bit more than saying that you have an identity. It means that you've got an identity element 1 and the norm of it is actually 1, which doesn't come for free. You can prove that the norm of 1 has to be at least 1, but it's not immediately obvious that it's equal to 1. And you might have to renorm to get that. So let's have some comments on this. We won't always name the norm, just like you sometimes say let E be a normed space. Sometimes we'll say let A be a normed algebra. And that'll just mean that it's a complex algebra for us most of the time, and that there's a norm defined on it which makes it into a normed algebra, but we maybe won't bother naming the norm. And as I said, we're mostly focusing on commutative unital Banach algebras. It's very similar, being submultiplicative, as I said, to saying that multiplication is jointly continuous, which means essentially this, as a map from A cross A to A. There's a notion of bounded bilinear map, which you can find out about, which is pretty much the same thing. So here's an easy exercise. If in fact you're quite close to being submultiplicative, then you can fix the norm by multiplying by an appropriate constant, which is either c or 1 over c here, but I can never remember which. I have to work it out every time. If you multiply by either c or 1 over c, then it actually becomes submultiplicative. I think you have to multiply by c, because then you get c norm AB is less equal to c norm A times c norm B. And so that will then mean that c times the norm is actually submultiplicative. So that's an easy exercise. This is a slightly harder exercise, but I've given you the solution. If you're a normed algebra, so you are now submultiplicative multiplication, and the norm of 1 is wrong, then it turns out that it has to be strictly greater than 1, but you can fix it by renorming with this triple norm here, and that triple norm turns out to be equivalent to the original norm, and it's actually submultiplicative, and the triple norm of 1 is 1. So there are some easy fixes you can do if you start out slightly wrong in the first place. So we don't lose very much by putting these additional requirements on. It doesn't really change the topology of the situation, because we're just going to equivalent norms and fixing the problems. And now I mentioned subalgebras. A subalgebra, of course, is a subset which is a linear subspace and it's closed under multiplication. And you could talk about a unital subalgebra. If you had a 1 in the original, then you could have a unital subalgebra having the same 1 in it as the original did. That would be a sort of notion of unital subalgebra. So subalgebras are normed algebras. You can just restrict the norm, and it's still a normed algebra. Of course, if you want to take a subalgebra of Banach algebra and still be a Banach algebra, that means you want to be complete with the restricted norm, which means you must be closed. So closed means norm closed as a subset, and subalgebra as usual. So you can get new Banach algebras from old by taking closed subalgebras of them. Any questions so far on this sort of really introductory stuff? We haven't got many examples yet, except that I've told you some. But again, you should think of continuous functions, continuous complex valued functions on a compact Hausdorff space with uniform norm. That turns out to be submultiplicative. And we already know about the bounded operators on space. We know that the norm of a product is less than to the product of the norms when you compose linear maps, because we did that earlier. I think. If we didn't, then that's an easy exercise. So here are those comments again. If you're on a non-commutative uniform Banach algebra, you can do this B of E, and the only new fact here, compared to what we said before, is to talk about the composite of two operators. That's that the operator norm of the product. So the operator norm of S composed with T is less than to the operator norm of S times the operator norm of T. And that is a very easy exercise to check that. And then you've got continuous complex valued functions on X. And we know that's a Banach space. And so saying that it's a Banach algebra, the new content is that the uniform norm of Fg is less than to the uniform norm of F times the uniform norm of G. Well, we know that the modulus of f of x is always less than to the norm of f, and the modulus of g of x is always less than to the norm of g. So the modulus of f of x, g of x is going to be at most the product of the norms. Why don't we have equality there? Under what circumstances might you not get equality? So remember, there'll be somewhere in x where mod f of x is biggest, and there'll be somewhere in x where mod g of x is biggest. Because it's a compact Hausdorff space. So why can't you just say, find a place where f and g are biggest and then multiply? Exactly. They may have maximum at different places. So unless you can find a place where both of them take their maximum modulus, this is going to be strict inequality. But otherwise, you definitely get the lesser equals because obviously f is at most the biggest f can be and g is at most the biggest g can be. And now, from now on, I'll drop the subscript complex numbers. If I write c of x, I'm going to mean the complex valued version now, because we're going to do the complex valued theory. And if you look in the literature and look at my papers, I'll talk about c of x a lot, and this is what I mean, the complex valued ones. And we know that you can take closed subalgebras of Banach algebras and get Banach algebras. And one good source in a Banach algebras is to take closed subalgebras of c of x. And that always makes you into a commutative Banach algebra using the uniform norm on x. To call it a uniform algebra on x, we add a couple of extra conditions. We insist it's got the constant functions in, which is, of course, there's the constant function 1. So you've got 1 in c of x to start with, and that's the constant function. So the function that's constantly 1 is the identity element of c of x. If you multiply 1 by anything, it's still the same function. So to say that you can have all the constants in, well, since you're a vector space, that means you need to have 1 in. So you need the constant function 1 in A, and then because it's a subalgebra, that also makes it a vector subspace. That's part of the definition of being a subalgebra. And that makes it a vector subspace. And so then all the constant functions will be in. And then there's this further condition that says you should separate the points of x. To be a genuine uniform algebra on x, you don't want to have functions which always take the same value here as they do there. You insist that you separate the points of x. So whenever you take two different points of x, you can find a function in the algebra that takes different values at those points. And under those conditions, then, of course, uniform algebra is still, because I insisted it was uniformly closed, the closed subalgebra of C of x, meaning closed with a uniform norm. So that mod sub x, that's a uniform norm. And so we're saying that's the kind of closed I mean. And then that makes it into a Banach space and then a Banach algebra. And, of course, it's a commutative unital Banach algebra. Notice that the uniform norm of 1 is correct. I don't mind, by the way, whether you use which notation you use for the uniform norm. So you can use norm infinity or mod sub x. The advantage of the mod sub x notation is that you can sometimes use it for if you want to see how big is the function on some subset rather than on the whole space. So you could use mod sub something else to say how big does the function get on some subset or other. And of course, C of x itself does separate the points of your compact Hausdorff space because that's a rather easy deduction from Eurozon's lemma. You can always find enough continuous functions to be, well, you can separate closed sets from each other, and points are closed sets in a compact Hausdorff space. So you can separate points from each other using Eurozon's lemma, or an easy special case of it. Well, a special case of it. Okay, so C of x is what I call a trivial uniform algebra on x, though it's not really a trivial thing. But I sometimes want to distinguish C of x from other uniform algebras, and then I say that C of x is the trivial uniform algebra on x, and the other uniform algebras I regard as the non-trivial uniform algebras on x, and they often have different properties. Here's a good source of examples. You take a compact subset of a complex plane. So another way of saying that is x is a compact plane set. Plane set means it's in the complex plane. Then here are some nice examples. We've already got C of x. Let me imagine that x looks like this. It's now a subset of the complex plane, so maybe it looks something like this. Okay? Just a nice subset of the complex plane. Compact, so it includes its boundary. It might have some holes in it or not. This one has no holes in it. It's just a solid lump. It might be connected or not. It might have several pieces. It might have some holes in the middle. I've just drawn a sort of, this is a a typical connected compact plane set with no holes in. A of x, it's those continuous functions which are analytic, also known as holomorphic, on the interior of x. So you need to know a little bit of complex analysis to understand that. If you haven't come across analytic functions, holomorphic functions, then you might need to look that up just to be secure on it. But then P naught of x, you just take polynomial functions with complex coefficients. So something like a naught plus a1z plus a2z squared, and then you stop somewhere. You stop at some point. And the a naught up to an are in C. And that gives you a nice function of z. Now, of course, that's defined on the whole complex plane, but then you can restrict those functions to x, and you get a set of polynomials restricted to x. If x has got infinitely many points, then you can tell what the polynomial was from the restriction. If x has only got finitely many points, then you lose lots of information when you do the restriction, and you can't tell which polynomial it was you started with. Rational functions are similar, except you do rational functions. Rational functions are polynomial divided by polynomial. But you mustn't divide by 0. So when I say no poles on x, if there's any poles, they must be off x. That means that you mustn't be dividing by 0. So you want to have P of z over Q of z, where P and Q are polynomials, but must avoid division by 0. Now, all I have to do is write this word division. Division by 0. Now, some of these are already closed and some of them aren't. Let's have a look. They've got the constant functions in because one is... the constant function 1 is analytic everywhere. It's an entire function. It's holomorphic on the whole complex plane, so no problem there. It's also a polynomial, and of course that means it's also a rational function, and so on. So the constant function 1 is in there, and there's a polynomial function z, and that's in there as well, in each of those algebras I've just mentioned. And this function already separates the points. This is the one where z of lambda is lambda. You can think of it as the identity map on the complex plane, but we often call it the coordinate functional. That's just another name for it, but it's also the identity map. So z, we often use z or to mean either the identity map on the complex plane or its restriction to x, which would be the identity map on x. So you can think of z equals the identity map on the complex plane. Z restricted to x is equal to the identity map on x. But we often still call it z. And that's in all of those algebras, so they already separate points. They separate points, they've got the constants in, but some of them are closed already, some of them might not be closed yet. Let's have a look. A of x, that was the one which was continuous on the whole of x and analytic on the interior. Now it turns out that uniform limits of analytic functions are analytic, so that's a standard fact about complex functions. So it doesn't... So it's already uniformly closed. If you take a limit of things in A of x, they're still in A of x. So A of x is a uniform algebra on x. But polynomials and rational functions alone, not normally closed, for a variety of reasons that you can investigate. Very unusual for them to be closed. You can determine precisely those sets X. You can actually quite quickly figure out exactly which sets X these algebras are already uniformly closed. So what we normally do is close them. So you start with the polynomials, P naught of X, and we say, well, it's not closed yet, but if we close it in C of X, then, of course, if you take a subalgebra of C of X and close it, you'll get a closed subalgebra of C of X. And that's what you do. So P of X is the uniform closure in C of X, of course, and the same for R of X. That's the uniform closure of R naught of X in C of X. And what do you get? You get those continuous functions though that bit is automatic. You get those continuous functions which can be uniformly approximated on X by polynomials, and then the same for R of X. Those continuous functions on X, complex valued of course, which can be uniformly approximated by rational functions. And then you've got this set of inequalities. Obviously, polynomials, it's harder to approximate functions by polynomials than it is to approximate them by rational functions. So P of X is contained in R of X. R of X is a subset of A of X. Again, polynomials are analytic on the interior. So a quotient of two polynomials is analytic on the interior. So rational functions will be analytic on the interior, as long as you're not divided by 0, which you're not. And then uniform limits of analytic functions are analytic, and so you stay inside A of X when you take the closure of R of X, and R naught of X. R naught of X is a subset of A of X. You started with P naught of X polynomials contained in the rational functions contained in A of X. And then when you take closures, you get these other equalities. Any questions so far about these examples? These are lots and lots now examples of commutative Banach algebras, because you can take any set you like in the complex plane and you'll pick up all these algebras from them. And so you've now got lots of examples. Any questions so far? Okay, moving on. Here's another Banach space we used earlier. This time you mustn't use the uniform norm. We noticed earlier that this one wasn't complete with the uniform norm. So it's once continuously differentiable complex valued functions on the unit interval, as usual, one-sided derivatives at the endpoints. So when you differentiate your function, you ask for one-sided derivatives at the endpoints and the usual derivatives in the middle. And then you ask for the derivative to be continuous, and then your function is in C1 of 0, 1. And remember, the norm you need is to take the uniform norm of the function and add the uniform norm of the derivative. And that turns out to be, well, we said earlier that made it a Banach space. That was an exercise from earlier in the lectures. So that made it a Banach space. But it's also submultiplicative. And that's an exercise now. So again, you have to check that this norm is submultiplicative. So it's not the uniform norm anymore, so you have to check that the norm defined here is submultiplicative. And when you do that, you'll just use Leibniz rule, and you'll find you've even got a spare term left over. So it's actually quite, it's an easy exercise. So it's a Banach algebra consisting of functions. It's not the uniform norm. So we call it a Banach function algebra, meaning that we've made a Banach algebra with some functions, but we didn't use uniform norm necessarily. In this case, we didn't use uniform norm. Uniform algebras count as Banach function algebras, but Banach function algebras don't have to be uniform algebras. It's just any way of making algebra functions into a Banach algebra with some norm or other. Unfortunate clash in the literature. Some authors call uniform algebras function algebras. We won't use that, but there's a book at Browder called Function Algebras. And the book by Browder called Function Algebras, his function algebras are uniform algebras. Now suppose you start with a norm space and you want to turn it into an algebra. Well, you can just say, take any old norm space and then say, multiply anything you like together and get 0. That's called the trivial multiplication. And that turns any norm space into a normed algebra. It's rather obvious that the norm of xy is less root to norm of x norm y because we've defined xy to be 0, so the norm of xy is going to be 0. We call this a trivial multiplication, and it means that every complex normed algebra is also a complex... every complex normed space is also a complex normed algebra, and every complex Banach space can be treated as a complex Banach algebra in what looks like a rather silly way, but actually this does turn out to be a useful example sometimes. So it's not, you shouldn't forget about it because it gives you a good supply of, well, for every Banach space you've now got a Banach algebra, though it's got a rather silly product, and it doesn't have an identity element. However, if you do that and you would like to have an identity element, you can always add one in. And this is what we call the unitization procedure. So let's suppose you start with a complex Banach algebra which doesn't have an identity and you'd like to have one. Then what you do is you add one dimension in, you just form the direct sum, external direct sum, with C. So that means you've got ordered pairs. The first coordinate is in A, the second coordinate is a complex number. And we already know that becomes a Banach space. This is the norm 1 we mentioned earlier. That's norm 1 discussed near the closed graph theorem material. You're basically, you regard this, yes, that's right. You regard this as two different Banach spaces, and you add up the norms in the Banach spaces. But of course, the norm in A is the norm you had before. The norm in the complex numbers is modulus. So this is just a special case of that norm 1 we had before, where you add the norms of the two things. It's not the only one you can use, but it does have the nice fact that it's submultiplicative. When you define this multiplication. So what multiplication do you want? Well, you want 0, 1 is to be our identity. So we want A alpha times 0, 1 to be equal to A alpha. Once you know that, you don't have much choice as to what you do. You're pretty much forced into this formula. We want the old thing to be a sort of subalgebra of this one. We also want A0, we want to say that's behaving a bit like A. So we want A0 times B0 to be equal to AB0. Oops. So that you've got a copy of the original algebra in there. So you want a copy of the original algebra in there and something acting as the identity element. And once you ask for those, there's not much choice over what multiplication to use. this is pretty much, it basically follows now from the distributivity rules that you want. So you just start with this and do distributivity rule and note that you want bilinear multiplication and you don't have much choice. So you multiply the A and the B together, then the beta, which is acting like a constant, gets multiplied by the A and comes in to give you the beta A there. And the alpha, which is acting like a constant, gets multiplied by the B and brings you the alpha B. And those are the bits that are in A. And then you have to multiply the constants together, the alpha times beta, to give you the complex number that you have in the product. And then you have to check that norm of A alpha times B. You have to check that the norm is submultiplicative. And that's a nice easy exercise again. With that sort of one norm we defined above, you need that to be, the way I've done it there, I need that to be greater or equal to norm of A alpha times B beta, with the norm and product as above. And that's this exercise here. Where you have to, I've already told you the answer to that. What's the identity element? Okay, so combine the previous two examples and you get lots of Banach algebras where you can have non-zero elements whose square is 0. You can't do that with functions. If you square a function and get 0, then the function must have been 0 in the first place. So we now want to talk about characters in the character space. So if you've got a commutative algebra, it's got an identity element 1, then what's an invertible element? Well, because we're commutative, we only have to check multiplication on one side. Usually you have to check multiplication on two sides. Here we only have to check on one side. So A is invertible if the sum B in A, so that AB is 1. And then, of course, AB is equal to BA equals 1 because it's commutative. And this is what you'd normally ask for. In a general Banach algebra, you'd want it to work on both sides. But we're commutative, so you only have to ask on one side. Inverses, as usual, are unique, and we can write B equals A to the minus 1. And, of course, if B equals A to the minus 1 implies B to the minus 1 equals A, or in other words, A to the minus 1 to the minus 1 is equal to A. What you'd expect from finding inverses. And then you've got a set of invertible elements in A, which we'll call inv A. So that's just those things which you can invert. If you're dealing with matrices, you know what invertible matrices are. This is the same as usual there. If you're dealing with functions, typically you'll be dealing with something like the function shouldn't take the value 0 because you want to take 1 over it. So it's not always quite as simple as that. So here are those comments again. In the non-commutative case, you'd have to ask for the multiplication on both sides. The inverse of the inverse is the inverse. Inv A is then a group, and you've got this bijection from inv A to itself. And because A is commutative, it's actually a group homomorphism. So it's actually a rather nice map from the group of invertible elements to itself. And as I said, this is often the case, and it is true for C of x. It turns out that you're invertible in C of x, that's if and only if you don't take the value 0. That's because if you do take the value 0, you can't possibly multiply by something to get 1, because it's still going to take the value 0. If it doesn't take the value 0, you can just do 1 over the function and you're okay. It's still continuous. These other algebras I mentioned, much less obvious, but it turns out to be true for R of x and for A of x, but not for P of x, that the invertible elements are the ones which don't take the value 0. But for P of x, that doesn't turn out to be the case unless you've got no holes. When you have no holes, it turns out P of x is the same as R of x, which is Runge's theorem. But typically, if you've got a hole like this, here's an example with a hole. Then P of x is not equal to R of x in this case. And if you take z minus a point in the hole, you get something which is not invertible. So z minus alpha times 1 is not invertible if alpha is in the hole. This is not obvious stuff. There's more advanced theory that covers that, but that's something that might be interesting to know. Okay, I think we'd better stop there for today. So we'll finish off the Banach algebra material tomorrow, and then in the morning and then in the afternoon we'll have the discussion of measure theory.